Hi everyone, welcome at the first webinar of the Diabatix Summer Series, CFD Simulations for Thermal Engineers. I'm Gert-Jan, AI engineer at Diabatix, and I'm your host for today. For those of you who might not know me yet, I'm a mechanical engineer with a background in automotive engineering, and at Diabatix I'm the point of contact for most of our customers in terms of support engineering and point of contact for our customers who work with us as a service partner. Today I will enlighten you a little bit on the basic features about running CFD simulations in Diabatix ColdStream, and that's the first part of our Diabatix Summer Series, a series of webinars which we organize during the summer to learn you more about the basic features of our ColdStream platform. Let's have a look. There are 4 webinars in this series. First of these webinars is today. That's a CFD simulations for thermal engineers, where we will talk about how to set up cases. So basically the pre-processing of a case. In 2 weeks, we will organize a second webinar where we will post-process the simulations. By then they will have run, of course. In the middle of August, my colleague Reshma will enlighten you on how you can use the platform to design an easy cooling jacket. That will continue on one of the simulations that we will start today. And at the end of August, my colleague Dr. Van de Beek will enlighten you more on which type of boundary conditions you can enable when you would run design cases or CFD simulations. Today we will also cover already a few boundary conditions, but we will keep it with some basics today. Dr. Van de Beek will go more in depth about the more complex boundary conditions. For today, I would like to talk about 2 cases, one liquid cooled case and one air cooled case. You can see them on this slide. So the first case is an e-machine cooling jacket. It's a 3D printed cooling jacket which is pressed over a motor. This motor, an electric motor, is generating heat, and this heat needs to be cooled. For that, there is made a design, and we will simulate that design. Secondly, we will have a look for an air-cooled case. This is a heatsink which is developed for an amplifier. Amplifier is generating quite some heat and locally on very small surfaces, and there are 2 fans to cool all these electronic components. Just as a note, these 2 designs are designs made by conventional techniques, so by conventional way of engineering. For the first example, we will show you how to also create a design with Diabatix ColdStream in the 3rd webinar, as I said, and you will see the same in another webinar for this air-cooled case. But since today we will only talk about CFD simulations, I took some conventional designs. So we will start with the first one, the e-machine cooling jacket, and to introduce you to the case, I have prepared a few slides where we can run through the boundary conditions and the setup of the case. Once we have done that, we'll switch to the platform and I'll show you how to set up this case in Diabatix ColdStream. So here you can see the cooling jacket itself. How you can imagine this is placed over an electric motor, meaning so the electric motor is sitting inside here. We don't simulate the electric motor with it. You could do that, but it's not necessary in this case. In this case, it's simplified just as a heated wall, which you can see here on the red surface. The jacket itself is printed out of aluminum, and to be more precise, out of aluminum silicium 10 magnesium with a thermal conductivity of 103. The heat generation itself, as I said, is represented with a heated wall, and we apply a heat generation of 700 watts to this. And looking to the fluid domain that looks like this, then you can also immediately see how the conventional design looks like. So the blue region, which you can see here, is the fluid, and you have here an inlet slot and an outlet slot, and we apply some boundary conditions to the inlet. An inlet temperature of 51.5 degrees Celsius and a flow rate of 3.8 liters per minute. So that's it for the fluid side. Only thing that I need to mention is that the fluidum itself is just regular water. So let's immediately switch to the platform, where we come to our project page. And as you can see, I have already created a project for the summer series. Here we will categorize all the simulations and design runs that we'll do during the Diabatix Summer Series webinars. For today, we'll start with a simulation, e-machine, cooling jacket, and then you need to select the case type. There are two types. Either you run a design or you run a simulation. Design is if you want to create a design, so with generative design technology. Simulation is if you just want to simulate an already existing design or a design which you have created with Diabatix ColdStream on a different operating point, for instance. So that's a classic CFD simulation. We'll select simulation in this case, and we add a case, and then you can start the setup by clicking the Start Setup button and upload the step file. Then you select where you want to go, you browse to the right folder, and you select the step file and you populate it. What will happen then is Diabatix ColdStream platform will load the step file, and from here on you will be able to apply all your boundary conditions and make the full setup of the case before starting the simulation. Now, the step file itself is something that you need to prepare in your CAD environment. What need to be in there, for instance, for this case, you have seen already on the pictures how the case looks. We have added a cooling jacket in there as a solid volume, solid void. We have added a fluid volume, and of course the surfaces that you would like to add as boundaries. So in this case, it's the surface where we apply the heat and the surfaces of the in and outlets. So in this step file, you have the solid volume, the fluid volume, the surfaces for in and outlets, and the surface of the heated wall. Everything that is within that step file is loaded into the platform, and from there on, you can load your or you can apply all your boundary conditions. Voila. The geometry is almost there. What you can see here already is the region tree, and there all the regions which are in this step file are loaded, and just by clicking on them you can start defining them. You have also an add interface button. That's to add interfaces at certain surfaces or between two solids. For instance, to add an additional thermal resistance. That's one of the more specific boundary conditions, and they will be covered in the last webinar of the Diabatix Summer Series by Dr. Van de Beek. So we won't use it for today, but we will use some other features. Let's start with defining all the boundary conditions. So as you can see here, there are two regions added, the solid region and the fluid region. Let's start with the first one. You just click on it, and then you need to select what type of region is it. Is it a fluid region or a solid region? In this case, it's a solid region. You can give it a name. Let's name it cooling jacket, and select the material. Let's search for it. That's always bigger in a big database. And it's aluminium, silicium, tin, magnesium with a conductivity of 103. In this library, there are already a lot of materials. Of course, if you do have a specific material only for your company, it cannot be in our library, or not in our public library, let's say, but you can add that at a local level for your company. In the libraries, there you can simply add materials. Voila. So that's it for the volume itself. If we click on the arrow, you can see then that there is also a boundary at the cooling jacket. This is of course the surface which is representing the heat generation. So let's call it E motor, and the heat generation was 700 watts. And then of course you have the second region. This is a fluid region. And there was just water used in it. What you then need to do is select the turbulence model. You can choose within a variety of turbulence model. My experience learns that for this type of case, the best model to go with is K omega SST. And then again, you see two surfaces. One is the inlet, one is the outlet. This one is the inlet. You can define different type of inlets, a fixed flow rate inlet, a pressure inlet, pump inlet, fan inlet. In this case, it's a fixed flow rate inlet. The second case that we'll handle today, so the forced air cooling case, will work with a fan inlet. So let's go now with a fixed flow rate inlet. Let's give it the name inlet as well. And the temperature was 324.65. Now we also need to give the flow rate, of course. I forgot about the flow rate, so let's look back again for a minute. It's 3.8 liter per minute. Let's have a look in the platform. There we need to give it in cubic meter per second, so it says just 3.8 divided by 1000 divided by 60. And let's enter that 0.0000633. So that's it for the inlet. Then we only need to define the outlet, which is a pressure outlet. We'll give it a name again. And we just set it to 0 Pascal. Okay, so you see now 5 green check marks. That means that we have fully defined the case. Let's do a final validation. And we are now ready to submit the case. Once you click the submit button, you get 4 options. Basically, you can choose whether you want to run this simulation at a conceptual level or a detailed level. The difference between these two is the resolution. I certainly want to have it, I want to have this simulation at a detailed level. Conceptual level is running a little bit faster and with less computational resources to give you a good first estimation of the result. Detailed simulations do run on a higher mesh count to deliver you very accurate results. I want to have this one at the detailed level, as I said, and then you can choose between 3 options. You can do that with 100 credits, then you have the results in 1 day. So if you would come back tomorrow, we would have the results. You can do it with 50 credits, then you have the results in 2 days, or you can do it with 15 credits, then you have the results in 7 days. I want to show you the results in 2 weeks, so the speed is not really necessary in this case, so I would just go with detailed 15. I click OK, and it's running now. Once the simulation is ready, I receive an email and I can have a look for the results, but we'll do that together in 2 weeks in the second webinar. So that's it for the first case. Let's have a look as well immediately for the forced air cooling case. Okay, so let's first start again with some introduction about the case. This one is a bit more complex, a bit more solids, a bit more heat generation. We have now seen the basics, so we can go for a higher level now. So what you can see here is an amplifier. There are some electronics mounted in the green part here at the bottom side, and there are some fins at this green part as a heatsink. Heatsink itself and the casing, which is placed over the heatsink, are consisting out of aluminum 6061, and there is a plastic manifold in front of it, and in this manifold there are 2 fans with a filter in front of it. If you have a look from the other side, you have the electronics in this green box, and this box is covered with some cover also existing out of aluminum 6061. If you have a look from the back side of the full assembly, you can also see that there is some outlet filter placed here, just to avoid that the dust is going into the case. That's the same reason why there are placed some fan filters over here. So out of all these geometries, we have created the fluid region, and we start, let's say on left hand side, with 2 fan inlets. So again, in the step file that we have created, we have enclosed the volume of the fluid itself, and we have the inlet and outlet surfaces included into the model. Really important is at the outlet that you give the fluid a little bit more space, so don't stop right after the filter at the outlet. It's important that you give it a little bit more space to develop again. That will give you a better or more accurate results, let's say. About the fans or the fan inlets, of course, if you work with a fan, then you need to give a fan curve as well. I have put a table in here with the fan curve. In the Diabatix ColdStream platform itself, there are already a lot of fans implemented in the library. Of course, not all of them, and if you want to use a specific fan like I want to do in this case, you can simply add that one. I will also cover that when we are at the platform again. Voila, and last but not least, you can see the placing of the electronic component itself. You have 6 times a component of 12 watt. These are a few smaller components, and then you have the most challenging component, that's component 7, that has a heat generation of 150 watt, and that's placed on a vapor chamber in order to spread out the heat. This vapor chamber, we will not model the vapor chamber itself with all its physical behaviors. That's not necessary in this case. We will assume that it's just a very well conducting material. So we are back at our platform, and we will start with adding the fan curve before making the setup of the simulation, since you need to do that in the libraries. So you click libraries, and then you get an overview of the materials, fans and pumps, and manufacturing settings. Let's select the fans, and then on the right top you can add a new fan. So the name of the fan is 632 NU, and I will in the description I will put that is for the Diabatix Summer Series. And then you can add point per point. I'll quickly grab them with me again. I don't know them out of the top of my head. So the first point is at 0 flow rate, of course. There is a pressure of 90 Pascal, and you can, by doing so, at every point. Okay, so that's at a few more points. And the last one. Voila, so these are all the points. You can also add speed. This is yeah, something that you can find at the data sheet of the fan itself, and you can simply add the nominal speed there, which is 3600 RPM, and the nominal point, which is in this point, or in this case this flow rate with the corresponding pressure, and then you can add a fan, and then you can use this in all your simulations. So let's go again to the project page and add the new simulation. So we'll give it a name again, a cooling amplifier, and it's again a simulation. And you can again upload the step file. Once again, the platform is going to load this case with all the solid volumes that we put it in there and all the surfaces which we put it in there. What you will notice, if you open this step file, it will be available at the webinar page at our website if you want to try it yourself, or you want to look to the CAD file. But what you will notice is that not all the solids that I showed you are in there. For instance, the outlet filter and the manifold, they don't influence the simulation from a thermal perspective. So I decided to not make the simulation too heavy, to exclude them as real volumes or as real solids in the simulation. But of course, what we did is we subtracted them from the fluid in order that the fluid behavior is of course correct. So by that we go for the best of two worlds. So you can see now the fluid region and all the other regions. In the region tree again, you see it's a bit more complex, but that's of course no problem for the ColdStream platform. Let's start with the first one again. It's the fluid. Let's call it fluid as well. And you can select which type of fluid. It's just air in this case. And again, you need to select the K omega SST, or yeah, you need to select the turbulence model. And in my experience, also for this case, I would like to use K omega SST. And then you have all the boundaries as well. So this is the outlet one. It's a pressure outlet again. At 0 Pascal. And then you have the two inlet patches. Let me turn it a little bit so that you can see it. And this time we need to select the fan inlet. Let's call it fan 1 and fan 2. You need to put a temperature in there, and I will quickly have a look to my presentation again to what the temperature was. And it's just at 20 degrees, so 293.15 Kelvin. And then you can select the fan, and as you remind, it's 632 NU. And now the settings, or the fan curve that we just imported into the system, will be loaded. We need to do again, or we need to do the same again for the second fan. So fan inlet, we call it fan 2. It's of course at the same temperature, and we select the fan again. Okay, so we are ready with the fluid. Let's have a look for the next component, which is the heatsink with the fins in order to evacuate the heat, or to transfer the heat from the heatsink itself to the air. You click again on the region and you select the region type, which is a solid in this case. Let's give it a clear name as well, as I did in my presentation. That will help during the post-processing, of course. And you select the material, which was 6061 aluminum. You see you can have different options depending on the heat treatment that the aluminum had. This of course influences the thermal conductivity. In this case it's just an annealed one, so you select it, and you can see again that there are different patches. For that we need to turn to the bottom side. Let's quickly visualize them and turn a little bit, so you can see these are the 6 components with a heat generation of 12 watts. So these are all heated walls. You could also choose to do simulations with fixed temperature walls or external walls. It depends on how you want to define your heat inputs. So these are all 12 watts. Voila, and we have defined all the components which were on there. You remember there was a 7th component, but that one is not located at the heatsink directly. The interface between that component and the heatsink, there is placed a vapor chamber in between, and we will model that one as well as a solid. What you can see now is the casing, so let's select that one again and define it as well. Casing, and that's again the 6061 material. For rest, there are no boundary conditions at that casing, but since it's consisting out of aluminum and it represents a lot of contact surface with the air, I decided to include it in the simulations as well. Okay, then you have the next region, which is the electronics cover. So it's again a solid. And the last region, which is the vapor chamber then. So for this vapor chamber, you could choose to fully model the physical behavior in depth. Now, my experience for this type of simulations, that would be an overkill, we can easily just simulate it as a regular solid with a very high conductivity. And that's in general a conductivity of 2000 watt per meter Kelvin. So you can select it, and as you can see, there is another boundary on this one, and that's the biggest component. That's component number 7 with a heat generation of 150 watts. Okay, so let's validate the geometry again. And we can submit a case again. Just like in the first simulation, I get 4 options again. For this simulation, I really want to know the results already tomorrow. It's important that I know them, or let's say that it's important that I know them tomorrow. No problem. Then you just select the detailed 100 credits. And when I will be back tomorrow, I will be able to visualize the results. So I click OK. And the simulation is running again. So let's switch back to our PowerPoint. So that's it for today. We have covered the 2 simulations, or we have done the setup of the 2 simulations, the e-machine cooling jacket and the forced air-cooled amplifier. So we have done the setup of these 2 simulations, and in 2 weeks, in the next webinar, we will have a look to the results, and I will explain you how you can do the post-processing in a time-efficient way with Diabatix ColdStream. As I said in the beginning, there will be 2 more webinars in the Diabatix Summer Series, designing a cooling jacket and applying boundary conditions. So that will be more in-depth. Besides the Diabatix Summer Series, we also have a few other interesting webinars, and one of them is a webinar which I will give next week, and that will be about the design of battery cold plates. It's a very hot topic, let's say, at this moment, with the change to electric mobility. The demands for better cold plates is getting higher and higher, and we see that Diabatix ColdStream can play a big role in that. So feel free to register for that webinar as well, and for the other webinars at the Diabatix Summer Series. And since you are here, you know already where to register, but I'll quickly remind you that it's just at our website. In the meantime, I see that there are some questions from the attendees. Let me quickly cover a few of them since we are almost running out of time. One of the questions is if you would apply some thermal interface material between your component and the heatsink itself, can you include that thermal resistance in the simulations? That is possible, and that's one of the topics that will be covered by Dr. Van de Beek in the last webinar of the Diabatix Summer Series. And Lydia is asking if she can receive the CAD files which I used today. That's not a problem. They will appear later on at the webinar page of this webinar, where you can easily download the step files and where you can find an overview of all the boundary conditions. I see there are a few more questions. I won't handle them all today, but I'll make sure that I get back to you in person to answer them, and I will summarize them as well in the next webinar of the Diabatix Summer Series. By that we can cover them all. If you have any questions which you haven't asked yet in the chat box, don't hesitate to do so. Then I can cover them as well next time. Or just drop me in an email or contact Resma in order that we can answer all your questions. So that's it for today. I hope I can welcome you again next week in the webinar about the design of the battery cold plates, and the week after that, so the 30th of July, for the second webinar in the Diabatix Summer Series. And in the meantime, I would say enjoy the summer. Thank you very much for attending.